In this section, we'll talk about writing complex numbers in polar form using Euler's formula. In the 18th century, Swiss mathematician Leonhard Euler made a connection between exponential functions and the sine and cosine functions involving complex numbers. That connection is known as Euler's formula. Euler's formula states that e raised to the I times theta power is equal to cosine of theta plus I times the sine of theta. Therefore, by direct substitution, z equals x plus yi, we know is the rectangular form of a complex number. We saw that if we substituted the values for x and y, which were r cosine theta and r sine of theta, we would come up with the polar form of a complex number, which equaled r times the quantity, cosine of theta, plus I times the sine of theta. Notice that that cosine of theta plus I times the sine of theta is what Euler recognized was equal to e raised to the I times theta power. Therefore, by substitution, we can say that z is equal to r times e raised to the I times theta power, and we call that the polar form of the complex number using Euler's formula. Now, question, why do we want to convert to polar form of a complex number using Euler's formula? We saw that we could write it in rectangular form. We saw that we could write a complex number in polar form. Why go one step further and use Euler's formula? The answer is because in this form we have multiplication. Notice that the rectangular form deals with addition, the polar form deals with addition. The polar form using Euler's formula is the only one that is written in multiplication, and that is going to serve a purpose when we go to find roots of complex numbers. We'll look at those in a little bit. Now let's look at an example that incorporates all of the different forms of a complex number that we've looked at so far. Complete this table and state the angles in exact radians if possible, where the angle is between 0 and 2 pi, including 2 pi, but not 0. All right, so in the first column, we see the rectangular form of a complex number listed as z equals x plus yi. We know that formula well. And the polar form in the second column of a complex number is z equals r times the quantity, cosine of theta, plus I times the sine of theta. And then finally in the third column, we also have the polar form, but now we're using Euler's formula and rewriting this as z equals r times e raised to the I times theta. So in those columns, everything that is below will be in that form. And our job is to fill in the blanks. Okay, so let's start with the first one. It says z equals the square root of 3 plus I. So in this example, we are saying that x is equal to the square root of 3 and y is equal to 1. Well, this example we actually looked at in a previous video, and we came up with the polar form of a complex number being z equals 2 times the cosine of pi over 6 plus I times the sine of also pi over 6. So refer back to that video if you want to see the work that went behind that. Now I'm going to take that and I'm going to rewrite that in Euler's formula. All right, so the r has been given as 2, right? The r has been given as 2, and the theta has been given as pi over 6. So I'm going to say z equals in Euler's formula r, which is 2, times e raised to the I times theta, which is pi over 6. And that's it. All right, let's go to the second row. We have the rectangular form z equals 1 plus 2i. So in this example, we are being given that x is 1. We're being given that y is equal to 2. If we were to plot this point, we would be plotting the point 1, 2, which is in the first quadrant. So we're going to make sure that we get an angle in the first quadrant. And our first job is going to be to find r and theta. So we're going to use x squared plus y squared equals r squared to write 1 squared plus 2 squared equals r squared. So that's going to give me 1 plus 4, which is 5. And I'm going to say that r is equal to the square root of 5. Okay, so let's see here. I'm going to have z equals the square root of 5 times the cosine of something. What is the angle that goes with this point? Well, this is not an angle measure that I think we have memorized. So in this case, it won't be possible to give exact radians. We'll have to do some rounding. So the angle, I'm going to go ahead and use tangent because tangent's been given to me. I'm going to say, and let me change colors to keep this separate. I'm going to say that tangent of theta is going to equal my y value, which is 2, over my x value, which is 1. And so theta is going to equal whatever tangent inverse of 2 is. And when I put that into my calculator and made sure that I was in radians, I got approximately 1.11 radians. Now, before we go any further, let's ask ourselves, is 1.11 radians, is that a first quadrant angle? And the answer is yes. You know, going halfway around is, let's just draw this out real quick, and I'm sort of creating a mess, but I think that this might be helpful. Going halfway around is pi, and pi is 3.14, right? This is 3.14. Pi over 2 is half of 3.14, which is 1.57. So a theta value of 1.1 we can see is somewhere in that first quadrant. Okay, so that confirms it for me. So I'm going to go back up here and I'm going to input 1.11 as my theta, and I'm going to write plus I times the sine of 1.11. Okay. For Euler's formula, I know the r and I know the theta. So in Euler's formula, I'm going to say that z is equal to the square root of 5 times e raised to the I times 1.11 power. All right. Okay, now in row 3, now we aren't given the rectangular form, we are given the polar form and asked to rewrite that in rectangular form and in Euler's formula. All right, so in this example, the 2 is in the position of the r. So I'm going to say my r value is 2, and my theta value is 2 pi over 3. So probably the easiest way to go is to rewrite this in Euler's formula. So I'm going to say that this is equal to, z is equal to my r, which is 2 times e to the I times theta power. And theta, of course, is 2 pi over 3, and that's it. To write this in the rectangular form, I need to find out what x and y are. Now remember that x is simply r times the cosine of theta. So this is going to be 2 times the cosine of 2 pi over 3. Notice that to find out what the x value is, all that I'm really doing is multiplying or distributing this 2 times the cosine of 2 pi over 3. What is the cosine of 2 pi over 3? Let's see, the cosine of 2 pi over 3 is negative 1/2. So my x value looks like it is negative 1. My y value, okay, the y value comes from taking that 2 and now multiplying it by the sine of 2 pi over 3. So let's see here. So 2 times the sine of 2 pi over 3 is 2 times, let's see, sine of 2 pi over 3 is square root of 3 over 2. So I'm going to call that just the square root of 3 because the 2 on the top and the 2 on the bottom cancel out. So in rectangular form, z equals 2 times the cosine of 2 pi over 3 plus I times the sine of 2 pi over 3 turns into z equals my x value, which is -1, plus my y value, which was square root of 3, with an I hooked on. Now, having that I to the right of the square root of 3 or having it to in front of it, either way is fine. Either way, just make sure that if you write it the first way, that your square root symbol over the 3 doesn't find its way over to the I. That I should be separate. All right, and now the last one, z equals 3 times e raised to the I times pi over 2 power. That's Euler's formula. And in that form, we see that the radius is 3 and that the theta is pi over 2. So writing that simply just as the polar form, I'm going to say that z is equal to the radius of 3 times the quantity cosine of pi over 2 plus I times the sine of pi over 2. I'll close that off. And if I multiply that 3 through, I get that z is equal to 3 times the cosine of pi over 2. Let's see, the cosine of pi over 2 is 0. So it's going to be 3 times 0 plus 3 times sine of pi over 2 is 1, and that's going to be I. So this is going to be z equals just 3I. So that's an example of a purely, what did we call that? Purely imaginary complex number.